Greetings, I'm Blackjack Fitz, and the puzzle that you see on screen right now is one of mine. It's called Slow Snake Somedoku, and I've had a number of requests for a walkthrough of this puzzle solution, so that's what I'm going to be doing in this video today. Let's go ahead and read the rules. We've got normal Somedoku rules, which means that we're going to fill each cell with a digit from 1 to 9, and then we're going to fill every row n and column n with exactly n different digits, repeating digits as necessary. So if we imagine that in row 5 we had identified 1, 2, 3, 4, and 5 in these positions, then the rest of the cells would have to be from 1, 2, 3, 4, and 5. That's because we're in row 5, so we only get 5 different digits, and we've already identified those 5. So the rest of these cells have to be repeats from the numbers that we've already identified. Now, if we're looking at row 7, we would need 7 different digits and 2 repeats. And the same will be true for the columns. If we get 5 different digits in column 5 that is, then we have to have 4 repeats as well. So that's how sort of Somedoku rules work. We've also got standard crop key rules. So these white dots separate cells that are adjacent or one number apart from each other. So if, for example, this was a 2, this could be a 1 or a 3 because 1 is next to 2 and 2 is next to 3 on the number line. And then digits separated by a black dot are at a 1 to 2 ratio. So that means that one digit's double the other. So if we knew that that digit was a 4, this could be a 1 or a 4 because 2 is double 1 and 4 is double 2. And we just need one digit to be double the other. Now we get into the sort of snake part of the rules here. So we're going to draw an orthogonally connected one cell wide snake that does not branch or touch itself, not even diagonally. So let's take a look at what that means. Let's say we had a snake that looked like this. Well, maybe let's do that. So let's imagine that that was our snake here. That would be an acceptable way for the snake to sort of function because it doesn't branch. So what that means is it doesn't do something like that. That would be a branch from the snake. That's not allowed. It doesn't touch itself. So what you couldn't do is have something like this. You couldn't imagine the snake doing this. You couldn't do that kind of thing, right? Because now these two cells are touching orthogonally. And that's not allowed. So, and they can't even touch diagonally. So that this cell, for example, we couldn't do something like this because even though these two cells aren't touching orthogonally, they're not sharing an edge. They are touching at a point, and that's not allowed by the rules either. So that's an acceptable snake, though. We do learn by the rules that all of these yellow diamonds, there's 4 of them in the grid, those are in the finished grid all going to be on the snake. Then we have a couple of rules about the snake themselves. So the first is that the digits along a snake must either increase or stay the same from one end of the snake to the other. So we could get something that looked like 1, 1, 1, 4, 4, 4, 4, 4, 6, 8, 8, 8, 8, 9, 9, 9. Something like that. It's basically a slow thermometer. So that means the digits can never go back down from one end to the other. So there, you can see here that they're always either, as you progress from this sort of tail all the way to the head, the digits either stay the same, like they do here with the ones, or they get bigger. And that's the only sort of movement that they make as they progress. And then finally, we've also got like a counting circle rule on the snake. So what this means is that any digit that appears on the snake tells you how many times that digit appears on the snake. So in fact, we couldn't go 1, 1, not just because it breaks the white dot, but because that would be putting 2 ones on the snake. But we could do something like this. And what you can't do is like that. Even though this is works for the slow thermometer, and we have 1, 1, and 2 2s, we actually have to have 3 3s. So both of these would have to be 3. Once we get a 3, we need 3 3s, right? So then if we knew that these were 4s, we would need 2 more 4s, and then all of those could be 6, And that would be a sort of valid way that we could potentially fill in this snake, ignoring the sort of yellow dots that aren't on it. And, well, actually, I think the rest of that work. Oh, no, there. That's broken too. But ignoring the sort of some of the clues in the puzzle, that's one plausible way of drawing the snake in this grid. And that's all the rules. There is a link to the puzzle in the video description. I would encourage you to give it a shot yourself first. But I'm going to go ahead and solve this now. So if you get stuck, you can sort of find the point at which you get stuck, try to get yourself unstuck, and then go ahead and try to proceed with the puzzle again yourself. So the first thing I'm going to do is actually highlight all of the yellow diamonds, and I'm going to make those snake cells. So I'm going to use this sort of dark green for my snake, and then I'm going to use red to identify cells that I know aren't snake as we sort of find those here. So the first step in solving this puzzle is actually going to be to recognize that this cell in row 9, column 9 is particularly restricted. And that's because row 9 and column 9 both work like traditional Sudoku, in that all 9 of the digits 1 through 9 have to appear in this column, and all 9 of the digits 1 through 9 have to appear in this row. And this has to move orthogonally. It has to sort of get out of this corner into one of these two cells. But it's inevitably going to pick up another, or it's got to change digits, right? So if let's imagine it went there. If it goes there, we've got, it can't also go here, because then we would have 3 different digits in a row, right? So this couldn't be that, and it couldn't be that. So basically the point is, this has to be a 1. And once it's a 1, you can't have another digit sort of further along the edge, because that's the lowest digit in the puzzle. Now, it's going to be going into either here or here. We don't know which, but the point is, let's imagine, we'll call it A. Whatever the next cell on the snake is, it's A. Well, now A has to be bigger than 1, because we have our 1, 1 that can appear on the snake already. And so the point is, whether it goes here or here, it can't grow in row 1 or column 9, because this has to be a different digit by the Sudoku rules, right, of the fact that we need all of these to be different digits. But it can't be, by the snake rules, it needs to grow into the same digit again. Because if, for example, we put a 3 here, and the next cell on the snake is a 3, then we need 3 3s. The 3s can't go any old where on the snake, they have to go in order, right? So we're gonna end up with this sort of sequence. Now we don't know that that's a 3, but whatever the next cell is, we're calling it A, needs to be at least 2 long. And so what that means is that that actually has to be A. Because if it's here, it has to grow out of this column into there. And if it's here, it has to grow out of the row into there. So one of these two is going to be on the snake. We don't know which. And then that's going to be on the snake as well. Now, I want to think about how we can sort of enter into column 9 or row 9 again. And the point is, it's actually very difficult. And that has to do with the way that snakes move. So if we imagine this cell trying to sort of come into this, into column 9, and then leave column 9 again, it can't, by rules, just do this, right? It can't do a tight turn. It has to make a big C pentomino turn at a minimum. So let's look at this and ask whether that's possible. And the point and this actually breaks, I think, hopefully pretty clearly, because all 3 of these have to be different digits. And that means that this digit can't partner up with there, and it can't partner up with there, so it is by itself. And that means that it would need to be a 1, but we already have our 1, 1 on the snake. And that's because every group of numbers on the snake, they're all grouped together, right? Hopefully you were able to see that from the example puzzle. So this doesn't work, right? We can't actually come into this row and do that. But we do have a cell here. And the way that we get this cell here, the way that we sort of avoid breaking the puzzle like we did over here with the C pentomino, is to recognize that we can get back into row 9, but only if it's the other end of the snake. So this cell can't actually turn here because it would have to be a different digit. And then what does it do? Well, now it has to grow again, but it can't because that has to be a new digit. So we'd end up with this sort of string of 3 again, one digit in the middle that breaks whatever you want to do. So the only way for this to enter into row 9 is if this is the other end of the snake. And it can't come from there, right? It can't come in from the side. So in fact, we actually get that that cell enters it too. And now we actually know that none of these other cells in row 9 or column 9 can be on the snake because we would have to do this big C pentomino turn thing. We've identified the sort of head and tail of the snake as these two positions here. So now we have to just find a way to connect them by reaching these sort of various diamond cells and whatever other rules of the puzzle make sense. Now, if we turn our attention to this cell, we'll see that this now can't be an end of the snake, which means that it has to be a corner of the snake. So both of those become snake. This, now it can't sort of do a tight turn on itself, so that's off the snake. So both of these become snake as well. And now we have to think about this stretch of 3 digits and ask, how does that work, right? And the reason that it works in column 8 where it didn't in column 9 is because we're allowed to have one repeat in column 8. So we could, for example, let's say this was a B and this was a C. Now we can sort of get out of jail by having C extend out this way, having B extend out this way, and that can be either B or C, and that's allowed. Right? The problem was that this digit was a separate digit, something else, right, D, when we were thinking about column 9. But that doesn't have to be true here. This can be a repeat. And in fact, it must be a repeat. This must be B or C in this context, right? Right, so that actually tells us how this works down here, because now we have our one repeat here, so this can't be double A that way. So this is not our other A that exists here. So that's A. We don't know that it's a 2 just yet. Actually, we do know that it's a 2 just yet. And that's because it can't, if you think about, if we wanted to make this more than 2, where would we put the other A? Well, it can't go there because we have A, that's our only repeat in this row. So it can't continue to grow there, and it can't grow up here because we've had our one repeat up there. So in fact, we get that A is actually a 2, which is quite nice. And this now is off the snake. This cell, which I'm going to denote, I'm going to make this A now. Since I just gave up my A, I no longer needed it for the 2's here. This is A now. A can't turn here, right? A is different than this cell. This is actually all B's by Somedoku logic, so let's go ahead and put those in. That's because we knew that this was B, which means that it's the only digit that can appear in row 1. And then once you fill that in with B, then that's the only digit that can appear in column 1. So if this is your first time looking at a Somedoku, this is always going to be true for this rule set, that all of these cells will end up being the same digit. So those are all B. So now this A can't sort of turn into there, and it can't turn here because we have our only repeat. And we know it's got to be bigger than 2 because we already have our 1 and 2, right? So that's got to be an A growing up there. This is not on the snake. The other thing we can do is think about this now isn't the last digit of the snake. So the most that B can be is an 8. If A is 9 and B is 8, and this is the end of this sort of snake like that, then that's then 8 is the biggest B can be essentially, right? And so we can actually do some work over here in ruling snake cells out of this as well, because all of the B's have to be together according to the rule set. So if we grow B as big as we can, assuming that that's C, we could go 1, 2, 3, 4, 5, 6, 7, 8. and that's as far as it could get. So none of these can be on the snake. In fact, this one can't be on the snake because it would be sort of cul-de-saced in. So we are left with that sort of pattern here. Now, if we think about what number C can be, well, it definitely has to grow. Even if that's C, it can't be 2. We have our 2's already. So C has to grow, and it can't grow there because we have our repeat already. That is the repeated digit. So that can't be on the snake because the next cell is going to be a C. And now C can't be, even if that's B, right? C can't be, well, even if that's C, 3 doesn't work because 3 would need to be right after 2. We've got all these cells to fill, right? So C has to grow, and it can't grow there because these digits are not identical. They're 1 apart. So in fact, C grows there. And we can do one better. We can actually make that a C also. And it's because if we imagine this as not a C, and we say, okay, well, let's make that cell, imagine that cell C. We can get it to 4. But now between 4 and 2, we only have 3 cells to play with, the 3 3's. And we just can't connect these in only 3 cells. It's not possible. You need 4 in order to do it, no matter how you sort of manipulate it. And so that has to be C also. And now we can ask what's going on down here again in this corner. Sorry, I just realized that we can make that red because otherwise it would be touching at a diagonal. So I'll do that and extend this while I'm thinking about it. Now I want to return back down to this corner because we end up with the same pattern that we got with this 2. And that's because whatever we make the next cell, which I think we can do like D's, corner mark D's, one of these is a new digit bigger than 2. And it has to be in one of these 2 cells. Well, if that's D, we have our repeat here, so it can't grow. It has to take that cell, this cell. And if this is D, then it also definitely can't grow that way because of the white dot, but also because of our repeat. So it grows that way. So no matter what, actually, we get that that's a D, and that's on the snake. But we can actually rule this cell out pretty quickly from being D because we have our 2 repeated digits in column 7. So if you imagine this is like one block of, this is like one number, because we know that this will be just one, the same number 3 times. And you count up how many different digits you can get here. Well, that's 1. Those 3 C's are 1. Then we could go 4, 5, 6, 7, 8, 9. Or sorry, so 1, 2, 3, 4, 5, 6, 7. And we need 7. So that means that all of these have to be different digits. So that can't be a D. This has to be D. And it has to be on the snake. Now, this is now off the snake. This can't turn in because that wouldn't work, right? Hopefully you can see that just from sort of the snake growth. That's now off the snake as well. Both of these are off the snake because it would be touching orthogonally if you came in there. We also can't dip down into this because it's the same sort of thing. We would have to make like a C pentomino to get into here. And inevitably this would need to be 3 different digits because we already have our repeat, so we couldn't have any repeated digits in here, but then that cell would break, right? So we can sort of do that as well. Now, this is an important step here, and it's to ask about this position in row 2, column 7. And that's because we know that this has to be a different digit because we have all of our repeats. So this can't be B or C, right? Or D or whatever, right? So that's some new letter. We'll make it E. But the point is now in row 2, we have a B and an E. So we actually know this can't be C anymore. So that is B. In fact, that is now E because we have it's just B or E. All of these are B's or E's, right? The same way that all of these are B's and A's. And E and A could, at this point, I think still be the same digit, so we will have to be a little bit careful there. I'm gonna, I'm gonna be a little bit of careful there. But we do know that this is different than B, which means that that has to be B, and this actually has to be B also, because these have to be different digits to be next to each other on a white dot. Right. So we're at this position now, and what I want to ask is, well, can this close? And because we have all of our repeats, that can't be C or D. So that can't connect, and that can't be a new letter and be on the snake. So that's definitely not on the snake. So both of these have to grow now. This has to be a D, because D can't be only 2 length. It has to be at least 3. And C now, 4, has to grow also, because this can't be 4, because that 4 would need to be connected straight to the 3. So that becomes C, sort of just like that. Now, we're at a position where, first of all, we have all of our repeats in row 7. So this can't be an A anymore. So that has to grow and be A. And for my next trick, right, so now we're going to be thinking about whether this can grow here or if it has to close there. So hopefully you can see we're in a position where because we have all of our repeats, well, that can't be on the snake, right? It could grow here if it was a new digit, but then that new digit can't grow there because we already have all of our repeats in row 7. So if the snake does grow into this position in row 7, column 5, then it has to be a new letter. So I think we can use F here. And let's try to imagine what that would look like. Well, that's 3, so F needs to be at least 4, and that's just not possible, right? If we were to try to make F 4 and take those 4 cells, then C would only be 4, and that wouldn't work. So we actually can't take that cell. We have to close it here. Now we have to prevent the snake from touching itself, including diagonally, making all of that not snake cell. And we're left with this being either C or D. And that means that this could either be a 4-5 situation, or it could be a 3-6. If this is C, then we're at 3-6. If this is D, then we have 4-5. But that is the only way that can work, right? It has to be one of those 2 configurations. Now, we get to the sort of really cool part of this puzzle, which involves using bishop's moves to count, to identify the length of the snake, which is going to tell us something about the number of odd digits on the snake. So let me try to explain. We know the two tips of the snake. We've got row 9, column 9, and row 9, column 2 as the sort of head and tail of the snake, and then some number of digits in between them. But we can use the fact, the sort of bishop's move, to identify the polarity of the length of the snake. Allow me to explain. If you think about the way a bishop moves on a chessboard, it sort of only moves diagonally, right? The sort of bishop that's on black always stays on the black squares. The bishop that's on white always stays on the white squares. And they sort of move in this sort of diagonal pattern, and they never actually cross each other. So that could be another bishop, right? And it would do, you could do like this. Oop, not like that, sorry. Like that. Like, and then this would be something like this. Dang it. Right? So you can see that they're on opposite sort of patterns in the grid. And so what that means, or you can use that fact, basically because we're having to step through the puzzle making orthogonal connections, that every sort of like odd step is going to take you to a different bishop square. So if you think about, imagine moving from this 1 to this 2. That's on the same bishop square, and so the length of it's going to be 3. And that's true no matter how you get there. Let's say you took a route that went like this to get to that square, right? Then you could count it, and it would always be odd. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. It's always going to be odd, and that's because each one step takes you to the other color of the bishop squares. So to get to the same bishop square, it's an odd length snake, right? Now, if we look at the two kinds of snakes here, we can see if we sort of try to move like a bishop, you can see that they're on opposite bishop's colors. And so that means that the snake is going to be an even length. And we can sort of test that, right? If we just sort of went directly there, 1, 2, 3, 4, 5, 6, 7, 8. 8 to get there. But let's say we added like a little zig, just a little zag up into row 8. Now we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can play around with this if you aren't familiar with it. You'll always end up having an even length snake to get to different sort of bishops, colors, squares. And so because we're sort of have this counting rule on the snake, and we know that the snake length is even, that tells us that we have to have an even number of odd digits on the snake. So think about the way that you can think about that is that it doesn't matter how many even digits you have on. That's not going to change the sort of parity of the length of the snake. But we need to have an even number of odd digits. So let's say we had no odd digits and only even digits. Well, then we would end up with an even length snake. If we had one odd digit, we'd have an odd length snake. If we had two odd digits, we'd be back to an even length snake, right? And since we know that the snake has to be even in length, we know that we have to have an even number of odd digits. So if we look at our puzzle at this point, this is going to tell us something very interesting, because we have a 1, and then we have either in this sort of sequence of D's and C's, it either goes 3, 6 or 4, 5, right? Now, if it goes 4, 5, we skipped 3. If it goes 3, 6, we skipped 5. So we definitely, from the digits 1, 3, and 5, have exactly 2 odd digits, meaning that at the moment, the parity of the snake is correct. What that means is, moving forward from this point on, so not including all of this, we have to have an even number of odd digits moving forward. And we only have 7 or 9 remaining. So that means that we either have to have both 7 and 9 in the puzzle, or neither 7 and 9, in order for the parity to be correct to get us to this cell at the end. So if we think about having neither 7 and 9, then the biggest we could make here, if this was 5, if we did 5 and 4, right, then we can make this a 6 and this an 8. But if we count and we are as efficient as possible, we could go 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, 7, 8. We end up 2 short. So we can't have no 7s and 9s. We have to have both 7 and 9. That actually tells us straight away that this has to be 9, because that's the last digit, and we know that this is the end of the snake. So those are 9s. We have to have 7 somewhere. The question that we could ask, and this is, you kind of have to be able to see this here, but the question is, can we have like 8, for example? And the answer is no, because if we look at like 9s, let's say we tried to be as efficient as we could, right? We've got 4, 5, 6, 7, 8, 9, and then we tried to get 8s in, 1, 2, 1, 2, 3, 4, 5, 6, and we're already touching, and we don't have 7 B's yet. So 8's definitely off the line. But even if B's were 6, right? We went 1, 2, 3, 4, 5, 6, or like 6, right? Then we could go like 1, 2, 3, 4, 5, 6, 7 sevens, and then 1, 2, 3, 4, 5, 6, 7. It just doesn't work. So in fact, and you can sort of play around with different iterations of it, but that's being maximally efficient in terms of what you can do here. So in fact, we know that this has to be, B's have to be 7s here, because we have to have 7 on the grid. And now we know the E is either 6 or 8. So I'm going to get rid of the E's and just put 6 or 8 there. And since now we have 7 and 9 in this has to be a 7 or 9. It can't be 9 because we don't have 9 in the thing, so that has to be 7. We can actually do a little bit better now with our coloring, because we have 1, 2, 3, 4, 5, 6, 7 now is the max we could do. So both of those become not snake cells, because after 7 we go straight to 9. It's the only way that's going to work. And in fact, if you look at it, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. We actually have to be perfectly efficient here. So we can't have any wasted movements. So we're just going to have 7 7s and then 9 9s. And that's exactly how the rest of the snake is going to end, independent of what's going on over here, whether that's 3, 6, or 4, 5. Right. So now we actually have to think about the fact that we're going straight from 7 to 9. And that means that the 7, that can't be 7, right? Because even though we could reach that with 7, 1, 2, 3, 4, 5, 6, 7, we would be broken because we can't put a 9 in this row. So that's not able to be 7, right? So the 7 has to turn down somewhere into one of these sort of positions down here. Right. So how do we proceed from here? I'm trying to remember. I don't think that's it. 6, 7, 8. That's it. So all of these are 7s or 9s. Just be by the logic here. Now that means this has to be a 6 or an 8, and that's because along a white dot we have to have one even and one odd, and that's definitely an odd digit, so that has to be the even digit. Now that can't be on the snake because it's just 7s and 9s, and we can't sort of come back up into that cell, so that's also off the snake. And now we can't sort of go into here, where that would be like a cul-de-sacing our snake, so that's no good. So now we actually know that the snake has to traverse that sort of path through there. So 1, 2, 3, 4, 5, 6, 7, or 6, 7. But that's the end of that's the start of the 9s here. So that's a 9, and that's a 9. And if we count, we could go 1, 2, 3, 4, 5, 6, 7, 8, 9. So our numbers are looking good there. That 9 tells me that that's an 8. So now 7 and 8s are the only digits here. This 7 now can't sort of come through here because it has to be all 7s. So both of those become 7s. That becomes the snake. These are off the snake now. And now, let's see. We have 9, 7, and C here. So I believe, so this has to be 9 or 7 because C is not 9 or 7. Well, if that's 9, that's 8, and that's broken. So that's not 9, that's 7. And once we get that that is 7, we know that this has to be 6 because it can't be 8 the way the snake sort of works. So C is 6. We can go 1, 2, 3, 4, 5, 6. Those are all 6s. We get the 3 3s down here. And now we have 6, 7, 9 as the only digits here. So that becomes 6. That becomes 7 to be consecutive. This is now 6, 7, or 9, so that's a 6 or a 9. But if it's 9, that would need to be 8, which it can't be because of Somedoku logic. So in fact, that is a 6, and that now can't be a 7, so that becomes a 5. Now we have 5, 6, 7, and 9 in this row. So we can sort of do this, right? Let's go 5, 6, 7, 9 for all of these. We have our repeat already in column 8, so that can't be 6 or 7. That's a 5 or a 9. We have now, that's only 2 different digits in column 6. So 2, 3, 4, 5, and 6, all of these have to be, or all of these have to be different digits. So that can't be 6 or 7 either. It's also 5 or 9. This has to be consecutive with 7, so that is a 6, apparently. It's quite cool. Thank you. Now, if we look at this column 3, one thing that we know is that we have 7 and 6, but also this 9 has to traverse column 3 at some point. So the only digits in this column actually are going to be 6, 7, or 9, which means that can't be an 8. And we only have 7 and 8 in this row. So 6, 7, 9, we get rid of 5 as an option from there. This can't be 7 or 9, so that becomes a 6. This can't be 7 or 9 because we have our 1 repeat already with a 2, so that becomes a 6. And this, in the sign of the devil here, we have our 3s, so that's also a 6. Apologies for anybody who finds that offensive. It was unintentional, but we do get 3 6s here in a row. Now the 9s can't connect through any of these, so the 9 has to connect all the way over there, and we've actually completed our snake. The rest of the cells are not snake, and we can see that we've got 1 1, 2 2s, 3 3s, 6 6s, 7 7s, and 9 9s. And now the rest of the puzzle is going to be classic Somedoku logic. So if we come over here and we look at the digits we have left, I believe it's 3, 4, and 9. This row, that cell can't be a 3 or a 9 because we've had our repeats, so that becomes a 4. This becomes a 3, 9 pair. The 9 is going to go next to an 8. And the 3 can't go next to a 2 because we've had our repeat in the column. So it's going to be next to a 4, so that becomes an 8, 4 pair. Now this cell can't be a 1 from the row, can't be 2, 3, 4. It could be a 5. It can't be a 6, 7, 8, or 9. So it is a naked single 5, which I always love. That gives us, because we can't have repeats, that becomes a 9 in the column. Now, let's see if we can remember how to finish this thing. We've got 2, 3, 4, 8. 2, 3, 4, 8. So there has to be a 3 on this because you need an odd digit. So neither of these are 3. Right, this now can't be an 8 because we need all new digits. So that's not 8. So this isn't 8 because 8's not consecutive with 3. So we get a 2, 3, 4 triple. That becomes 8 here. Right. And now do this one. This can be 1, not 2, 3, 4, 5, or 8. 1, 3, 4, 5, or 8. This one can't be 3 or 8. This one has to be all new digits as well, so that's not 3. Right, so now when we look at this, neither of these can be 1 because they're not connected to a 2. So, and that can't be 8. So that actually is a 4-5 pair here, which removes 4 and 5 from these cells. This 8 would need to be with a 4, which it can't be. So that's not 8. 3 would need to be with a 6, which it can't be. So that's not 3. So we're left with 1, and that's 1 and that's 2. Now you might be wondering at this point why I used a black dot when it was a single. I could have had only white dots, and that's because if it was a white dot, that could have been a 3. So I didn't have a unique solution with just all white dots. It's kind of the one bummer I have about this, but that's fine. This is now a 5 or a 7 by white dot logic. Ready? So that's 1. This becomes not 1. That's 3 or 8. How do we do this? 7, 8, 9. This cell, possibly. It could be 1. It can't be 2, 3, 4. It could be 5. It can't be 6, 7, or it could be 8. 1, 5, or 8. So if that's 1, it's 2. I'm trying to remember how I did all this. We've got 1, 2. Oh, this can't be 3. That's right. That's important. That one can't be 3 because we have our repeats in here. So that is a 3, which means this isn't 3. And that now gives us all of our digits here: 1, 2, 3, 6, and 7. So we can actually do that like this: 1, 2, 3, 6, 7. But what? How did? What's the step here? 7. That can't be 7. So that's 5. Sorry, that's 4. That's 2. That's 4. That's 5. That becomes 9 because we have all of our repeats here. Now, we have 6, 7, 9. So yeah, this can't be like a 1. Right, if you think about the way that this works, 9, 8 would be 1 new digit. 3, 4 would be 2 new digits. So this can't be 2 new digits. This is either 2 repeated digits or 1 new digit. But so this definitely can't be 1. 2, 3, 4 doesn't work either because that's too many new digits. I was wondering if 2, 3, and 3, 4, because there was overlap on the 3. But 3, 4 means this can't be any new digits. So that definitely can't be 2 either. But 3, 4, and 3, 4 might work. Okay, but here we have a problem because 1, 2 doesn't work. We have 7, 8, 9 already. So 1, 2 would be too many new digits, so that's not 1. 5, 4, or 5, 6 would also be too many new digits. So that is 8. This is can't be 9 because that would have to be 8 again also. So that is a 7 actually, and that is a 6, right? So we still need 1 new digit in one of these two positions. That's fine. Now we have 1, 2, 3, 6, 7 here. This row is meant to be where we look. We got 5, 6, 7, and 9. That's only 4 digits. We need 2 new digits, so we can't do 9, 8. That's only 1 new digit. That has to be the 3 and the 4, the 9 and the 8. And now we have 6, 7, 8, 9 as 4 different digits. So we need 1 new digit along here. And it can only be 5, 6 because 6, 7, 8, 9 are all the sort of high end of the spectrum there. So to be consecutive with one of those digits and have a new digit, the only thing that works is 5, 6. That can't be 5, so that's 6 and 5. Now we have 5, 7, 8, 9 as our 4 digits here. So that becomes 8, and that's the puzzle. Thank you so much for watching. I hope you enjoyed it. There's definitely a tricky step there, but I quite like the way that sort of worked out. Even the sort of some of the tricky Somedoku bits at the end there. So, let me know how you enjoyed the puzzle. I would love to get your feedback. But yeah, thanks for watching. Appreciate it. Cheers.